Welcome to CS 101, Scientific Python, Lecture 15, on random numbers. Randomness is a property of the natural world around us. We're interested in explaining how we get random or unpredictable numbers generated from deterministic algorithms. In other words, the machine follows certain rules. We write these rules down as programs. But how, given a known program, can we generate unknown or unpredictable results? Our second objective is to distinguish the three basic random distributions: the uniform distribution, the normal distribution, and the discrete integer distribution, and to know when to apply them, or the kinds of circumstances in which they may be most useful to us. And finally, we're interested in plotting and interpreting histograms as these arise. Considering the following sequences of numbers. The first group of numbers contains things like 7, 8, 5, 3, 9, 8, 1, 6, etc. If I were to ask you to predict the next number in this sequence, would you be able to do so? In contrast, consider a well-behaved sequence of numbers. Here we have plus 1, negative 1/3, plus 1/5, negative 1/7, plus 1/9, etc. If you look at the denominators, you're able to clearly see a pattern of the increasing order of the odd numbers and the alternation of positive and negative signs. If I were to ask you to predict the next value in this sequence of numbers, you would say to me positive 1/17, and that would be correct. However, both of these sequences are derived from the same rule. One of them is the decimal expansion of pi-fourths, and the other of them is the series expansion of pi-fourths. One of them seems random to us. Truly random processes, such as wind speed, vary based on physical processes that we cannot model in detail. If I asked you to predict the third significant figure of the current wind speed reading, you would have no precise way of saying what that might be. It could be any digit with any degree of accuracy. Although physical random number generators exist, we prefer to use pseudo-random number generators instead, which are fast algorithms that can produce many random numbers quickly. These rely on an asymmetry in our knowledge to produce pseudo-random numbers, or sequences of values that we can't predict from outside of the algorithm. Most of the time, a random number generator needs a starting value called the seed. This is like choosing a point in the sequence above from which to produce random numbers. If we look back at the pi/4 decimal expansion, the upper series here, if we were to start at, say, the fifth digit, we would start with 8, 1, 6, 3, 3, 9, which is still just as unpredictable to us as starting anywhere else in this sequence would be. A seed is like choosing one of those locations. If we provide a certain seed, which is just a number, then the random number generator will always provide the same sequence, starting from that seed. If we don't provide a seed, then the machine will automatically use the current system time, and you will get an entirely unpredictable sequence. NumPy provides a submodule, numpy.random, which contains methods for generating random numbers drawn from different distributions. We can set the seed using the seed function inside of that module. We import numpy as np. We select a seed, something like 101, and we state np.random.seed and pass it that value. Now, any random numbers that we generate, and we'll look at a few different distributions in a moment, will be the same random number sequence that I see as what you will see on your computer. A fixed seed is very useful when composing code, so that processes that lead to errors when they vary don't vary while you're writing and testing your program. In summary, these pseudo-random numbers, what we will call random numbers from this point forward, come from deterministic computer formulae. The seed and the opacity in your knowledge about that particular sequence together make each new number unpredictable to you. These values can be transformed to generate dozens of possible distributions or ways of selecting random values.